Hi again, everyone. So, in the latest issue of the FAA's Airplane Flying Handbook, they dedicated an entire chapter, Chapter 4, to energy management. This is obviously an important set of concepts if they did that, and you're going to see it several times in your training. Next, we're going to talk about how the control inputs we use to fly the airplane as pilots interact with the energy state of the airplane. These are key concepts moving forward with a wide range of concepts from slow flight to stalls to flight planning, aerodynamics, and more. So let's get started. Before we do get started, we need to review the four forces of flight so that we know what these energies are acting upon. Of course, first, there is lift. Lift is what supports the aircraft in when we're flying it. It is countered, its opposite is weight. Then, of course, there's thrust. Thrust is what pushes or pulls the airplane forward, and the thing that counters that is drag. Anytime there's an imbalance between those forces, there's acceleration or deceleration in the respective axes, vertical or horizontal. For example, if there's more thrust than drag, the airplane is going to accelerate forward. If there is more lift than weight, the airplane will be lifted up. And of course, the opposites apply. A discussion on energy management starts with the conservation of energy principle. That reads that the principle of energy conservation states that energy is neither created nor destroyed. It may transform from one type to another. Now that's interesting. In essence, it means that one type of energy, say kinetic energy, the force that moves something, can be converted to, for example, electric energy or heat energy. Now, we're going to be talking about two different kinds of energy here. Kinetic energy, that's the force of motion, and potential energy, which is stored energy, in our case, in the form of altitude. There are two sides to the equation in this diagram. On the left, you have energy gained from thrust minus energy lost through drag, just like in the four forces of flight. You get a net energy change. If there is a change, we have to look to the right of the diagram and figure out if there's a change in potential energy, altitude change, or a change in kinetic energy. Now, advancing the throttle intuitively says that the airplane is going to go faster, but that's not necessarily the case. And we're going to talk about how you can invest that energy in either airspeed or altitude later on. This is a fascinating chart that introduces the concept of energy height. Now, energy height is a way of expressing your total energy as a factor of altitude that you have over your uh, altitude above ground level, because obviously the altitude below ground level, if you're at a high elevation, doesn't do you any good in an airplane. Your altitude in feet, vice your as a factor of your airspeed in knots. Now, there are constant lines here. If you look at 9,500 feet, we have a line that goes from, on the left, 9,500 feet and arcs downward as you accelerate. So if you were doing, for example, at point A, 6,000 feet actual altitude, doing 100 knots, you are at 6,500 feet of energy height. If you look down towards B and slide down that 6,500 foot energy height line, you can see that if you traded off 2,000 feet of altitude descending to 4,000 feet, you would, in a perfect world, be doing 250 knots. If you started out at 4,000 feet, 250 knots, you could raise your nose, climb to 6,000 feet, and be at the same energy height. Now, there's some X factors there, and there's some inefficiencies in doing so. So it doesn't really work out that way in exactly in practice, but it does illustrate the point that energy height is a factor of altitude times airspeed. This particular chart gives a little more context. It has the line of constant total energy that you saw in the previous chart, overlays it with the airplane's energy envelope. That's the amount of energy an airplane with its design, engine, and wings and such are capable of operating within. And then on that line of constant total energy, there's a point, which is point number 1 in yellow, that the airplane is supposed to be at. That's what the pilot intends, for example. Now, you can deviate from that by going up and down the blue and red line, which represents altitude, and the green line, left and right, which represents a decrease and an increase in airspeed, respectively, or a combination thereof. If you look at point number 5, the airplane is slower and lower than intended. It's at a very low energy state. If you look at point number 3, the blue point, it is higher and faster than intended, so it's a very high energy state. If you look at point 2, for example, the blue dot directly above point 1, it is on airspeed, but it's got more altitude. Now, what do you have to do to gain equilibrium on those? Well, point number 2, you're higher than intended. If you simply point your nose down to descend, you're not going to get the exact result you want because you're also going to pick up airspeed, like riding a bicycle down a hill. At that point, you're going to have to take away some energy that is otherwise gained by, for example, reducing thrust, right? Retarding your throttle a bit, pulling out your throttle so that you don't gain that additional airspeed. So there's always a balancing act, remembering the first chart about net energy that we saw earlier. So this is a balancing act that we have to maintain as pilots. We need to, for example, to get that constant airspeed descent to get from point 2 to point 1, we are certainly going to have to take some energy out, and that's via throttle. Adjusting the pitch, certainly, but reducing the throttle is going to keep us from getting additional airspeed because we are using some of that potential altitude energy to pull us forward. We're replacing the thrust with altitude energy momentarily. Once we get down to point 1, we're going to have to, and we're in level flight, we're going to have to reintroduce some of that power. So again, this is how pilots maintain the energy state of the airplane. And it's important to think of it and understand it like that.